So I'm recording starting now. So waves and optics. This equation is the wave equation. So it is actually one that spans both of these units, the optics unit and the duality unit, because obviously wave particle duality, this is relevant as well. In this equation, we've got three variables. Hopefully you know what all those mean by this point. I'm not going to go through all the units, et cetera. You can come back to this slideshow, which is being recorded, if you look at those things. But the key things that I want you to get out of this are, what are the relationships that are relevant here? Because you mostly use this equation sort of conceptually. So there is a linear relationship between lambda and v, which means that for a given wave, if its velocity increases, the wavelength is going to increase as well. I kind of use this car model. You picture these cars driving along, and the cars are the crests of the wave or something. And if those cars are driving along at a slow speed, they're close together. And as soon as they hit a zone that's got a higher speed limit, right, they end up spacing themselves out more to accommodate the higher speed limit. And so that's kind of how I conceptualize or understand that linear relationship. But the key thing, and this is down here in the notes, is the velocity of the wave depends only on the medium. So that spacing based on velocity is only going to change if the wave is moving from one medium to another through a wave boundary. So through a medium boundary. So the velocity of a typical wave does not change as it moves through space, and it doesn't depend on the frequency or the amplitude or anything else. It only depends on the thing that we're moving in. And when we shift mediums abruptly, the wavelength is going to be changing as well in a linear fashion. So higher velocity, higher wavelength. The second relationship has to do with lambda and frequency, and this one is a lot more intuitive to people. The idea being, if you have a really high frequency wave, if the wave source is jiggling really fast, the wavelength is small. The waves are close to each other. And when the wave source is jiggling slower, then we have the waves further apart from each other. So that's an inverse relationship, and that one should be more intuitive. There is no relationship between velocity and frequency because those are the independent variables. The only way you can control the velocity is by changing the medium, and the frequency only depends on the wave source. Lambda is the thing that links them and is dependent on both of those variables. Any questions on this equation? Hopefully you will type them into the chat or turn on your mic, which would be faster than typing things into the chat if you can. Typically, this is used for regular waves, but there are occasions when you have a de Broglie wavelength problem, if you've watched the duality videos, and you are asked to find the frequency of the de Broglie wave or something, and you would be using this equation with the v being the speed of light in that case. In the chat, how many of you have watched the duality videos just out of curiosity? I know you're not all taking the test yet, so not all of you will have watched it, but can you just give me a yes or a no just out of curiosity? Have you watched those videos yet? Okay, so let's move on. All right. This is the second wave video or wave equation that would be relevant. And this one, I would call this the index of refraction equation. It basically tells you this idea that the speed of the wave depends only on the medium. And to that end, all media have a characteristic index of refraction, which is this n value, and it's a material constant. So this is not something that changes. Glass always has an n of roughly 1.5, water is always 1.3. Plain air is basically about 1. Diamond is always 2.4. So each material has a set constant value, and we can use that constant value to basically scale the speed of light through that material based on the maximum speed of light, which is the speed of light in a vacuum, or c. So this equation is a pretty straightforward one. You're always going to plug in 3 times 10 to the 8th up there for c. You'll be usually given a value for n, although occasionally you'd be given a v and asked to find n or figure out what the medium is. And this allows you to calculate v. The one relationship that's relevant and useful to have in your brain is that n and v are inverse. So the bigger the n, the smaller the v, because it's essentially a ratio, right? It's a ratio of speed of light to that speed. So the bigger the ratio, the smaller the v value ends up being. So the larger n means slower light in that medium. And a note just at the bottom, n can never be less than 1, because that would mean that material will be faster than the speed of light in vacuum. And one of the fundamental tenets of physics is that's the fastest light can ever move. And so the typical range on like sort of typical naturally occurring elements is from 1, which is air. Air is just slightly more than 1. It's almost a vacuum, but not quite. But we assume it's the same as a vacuum. Up to 2.4, which is diamond. And so speed of light in diamond would be the slowest naturally occurring substance that it can move in. Questions on this slide? Okay, I assume you guys are going to turn on your mic and ask a question so that we can get through it quickly. All right. So these equations I'm going to go through fast because I'm going to come back to them at the end of the slideshow when we talk about concepts. But briefly, just so you have it all together, that equation, if you're looking at your equation sheet, is known as Snell's law. And we use this equation for calculating, oops, what just happened there? The Zoom. Come on. Okay. All right, sorry. All right, so we use Snell's law for calculating how much a light ray bends as it moves from one medium to another. So whenever you have two different media, we know that the speed of light is going to be different speeds in those media. If the light ray goes straight into the medium boundary, it's going to go straight through, but it's going to speed up or slow down. In this case, we're going to slow down as we get into a bigger value of n. But if that light ray hits the medium boundary at an angle, okay, then that light ray is actually going to bend. That is known as refraction. So this equation calculates, essentially compares those two angles. This would be the incident medium, Ni, and this would be the, or N1 and N2. This is the refractive medium, the second medium we go into. And so then this angle here measured from normal is theta I, and this angle here measured also from the normal line is going to be theta R. And obviously this is N1 and N2. So when you plug in these values in this equation, it tells you what those angles are. One note about this equation is that it can also be used to calculate what's known as the critical angle of a material, and that critical angle is the angle above which the light ray actually doesn't go into the new medium. So whenever you're going from like fast to slow, like we just did, the light ray always goes into the medium. Incidentally, some of that light ray is going to be reflected as well. But if you're going from slow to fast, big N to a small n, the light ray is going to be bending away from normal. And at some angle, at some magical angle here, that light ray actually skims on the surface. It bends so much that it actually goes on the surface of the boundary instead of going into the new medium. And that angle here, of course, is going to be 90 degrees. And so if you want to calculate this magic angle, this angle of incidence for which there is no refracted ray, the refracted ray stays on the surface, you plug in 90 degrees for that theta 2 value here, and you plug in your n values that you know, and that allows you to calculate what is known as the critical angle for a material. Questions on this slide? Okay. This equation is called the thin lens equation, and it's another high use, high bang for your buck equation. We use this equation for calculating the distance to objects or images or the focal length of an optical device. So typically a lens or mirror. So it's called the thin lens equation, but you can use it for lens or mirrors, curved, the ideally parabolic mirrors or lenses that have been well designed to have a discrete focus. In this equation, F represents the focal length of the mirror or the lens, and I'll come back to that in a minute or two. What does that mean? SI is the distance to the image, and SO is going to be the distance to the object that we're creating the image of. A couple logistical notes about using this equation that you definitely want to refresh yourself on. SO is always a positive value. We always assume the object is located in a positive portion of the optical device. F is sometimes positive and sometimes negative, and it's really important that you plug in the right value because you're going to get the wrong answer if you don't put the sign on your F. So in the problem, they will not give you a negative F. They expect you to know that yourself. They'll say the focal length is a certain distance away from the device, and you'll be expected to know whether you should be putting that in as a positive or a negative. So a negative focal length happens when you have a diverging device. So that means a convex mirror. So a mirror that, is doing this, right? Which means that light rays hit that mirror and they bounce away. Or a concave lens, okay, which also diverges things. So that's one of those lenses that looks like this. And when light rays go through that, again, they bend away or outwards. So these are called diverging devices, and they're always going to have negative focal lengths, no matter what they tell you in the problem. Other devices, converging devices, have positive focal lengths. So if I have that convex mirror where the light rays all kind of bounce right towards each other, right, that little location will end up being our focus. Or when you have the convex lens, okay, then the light ray goes through the lens and then it bends towards a single point, so it converges at a single location. Those are going to be the devices that end up with a positive focal length when you're using this equation. So make sure that you're careful about those sign conventions if you want to actually get the correct answer for SI. Okay, so usually you're using this equation to solve for SI. The cool thing about this is if you are careful about your sign conventions, not only do you get an answer for SI, like where is that image, but it also tells you something about the image. It tells you whether you are ending up with a real or a virtual image. If you end up with a positive SI value, it's going to be a real image, and if you get a negative SI value, you end up with a virtual image, which just means you couldn't capture it on paper. It's something that your brain is going to be inventing. Remember, like if you had an eyeball here and an eyeball here, it looks like those light rays came from this spot right here, but they never actually did. So that's a virtual situation. Whereas over here, we've got real images because those light rays actually cross, or my brain thinks they crossed at that location. So the cool thing is, like I said, this equation actually both works mathematically and kind of gives you a boost conceptually as well. Questions? Please turn on your mic and ask a question if you got one. Love to have a question.
Wait, so an object and a focal length can be on opposite sides of the mirror, but still be positive, or lens? Okay.
Thank you for that clarification. The positive and the negative have nothing to do with which side of the device that they're on, actually. And so that SI distance actually does not tell you if it's making an image on the left or the right. You have to use your own physics brain to figure out where that image would actually be. And it's because it's different on a lens and a mirror. On a mirror, we're making the image by bouncing back, and on the lens, we're going through. So you can't like just assume that we're going to get that will tell you whether it's left or right. So thank you. Yeah. Okay. And just like you said, the object could be located a positive distance, and the focal length could be positive on the opposite side of the device. So yeah.
Okay.
Great question. Okay, next slide. This equation is kind of a minor one. It's just a variable called magnification, and it works just like you'd expect it to work. If an object is 1 centimeter and we see an image that's 2 centimeters, well, magnification is 2, it doubled. And you can calculate that value either by the height of the image divided by the height of the object. So 2 divided by 1 gives me a magnification of 2. And similarly, the distance from that device to the object is it all works out with geometry. So if this is my object here and my image ends up over here, okay, if the ratio is 2 to 1 on their heights, the ratio of the distance away from those things, which I did not draw to scale, obviously, is going to be also 2 to 1. So 2 SO here. If the heights are HO and 2 HO, the distances away are going to be in the same ratio. This equation obviously usually gets used with the last equation when you figured out where those objects are located. This is the last equation that's in the optics portion of the equation sheet. So I'm throwing it on here, but it's actually in our duality unit, so I'm not going to talk about it, but I wanted it to just be up here just so you guys knew. This was a product of me reshuffling things around. Like this talks about like light, but to me, it doesn't have anything to do with lenses or mirrors or refraction or reflection, so I didn't actually include it in my optics unit. I included it in duality. So this is an equation that lets you calculate the angle between bright fringes on a screen due to 2-slit diffraction. If you haven't watched the duality unit, that means nothing to you. So I'm not going to spend any time going through it. I'll go through it again next week when we talk about duality. So hopefully, if you haven't watched duality videos, this would be a good weekend to do it because I'm going to be reviewing those concepts next week. Okay, so these are some slides. So sorry they have a funny extra image of me on them, but these are a handful of the critical slides that I pulled out from the optics slideshows just to save you the trouble of going back and watching all those videos. That illustrate some of the critical concepts from optics. So we have this guy right here, which is a good place to start, the law of reflection. The idea being that light acts, reflecting off a surface typically acts like a tiny particle or a little ball. And if you know what angle it hits the surface, it's going to bounce off at the same angle. The tricky thing about this is just remembering that we measure all of our angles from a 90-degree normal line from the surface, not from the surface itself. So wherever your surfaces are, you've got to first draw that line on there. And that's actually a little bit of a tricky thing to do sometimes if your brain doesn't work super spatially. So I drew a surface here, I drew my right angle here, and then if I wanted to figure out what this reflection looked like, I would make an angle on that side and the exact same angle on the other side of the normal line, and then I would draw that ray reflecting out downwards. So it's a good thing to practice on a little bit. I have here a right angle set of mirrors. This is the kind of thing that the AP will throw at you on occasion. I didn't teach what to do with it because there's an infinite number of permutations that you could put mirrors at different angles. But figuring out what's going to happen is just a product of using this law of reflection twice in this case. You've got the light ray coming in, use the law of reflection, and then it bounces off, and then you hit again, and it bounces off again. The neat thing about mirrors at right angles based on geometry is that these lines actually end up parallel. The incoming and the outgoing rays end up parallel. So these are actually used in industry quite a lot to reflect light straight back at a person, right? Because if, like, for example, on the moon, we have a set of mirrors on the moon that we want to use to figure out how far away the moon is. If you put a single flat mirror on that moon, you shine a laser on it, which we probably can do that. But if it's tilted even a tiny bit, right, the reflection from that laser could end up miles away from where my original sensor was. So from Earth, we want to figure out how far away the moon is. We want to shine a laser and have that laser come back, and then we're going to time it, is essentially how far away we can figure out how far away the moon is. But it's a big mess if that mirror gets off kilter, or my laser gets off kilter. So they have a right angle mirror on the moon instead, and then no matter where you shine the laser from, it's going to reflect that laser exactly straight back to the laser source. So that's what we have on the moon, which is kind of a cool detour there. Questions on this? Okay, yeah, this one's pretty straightforward. Ray tracing is the critical skill that you need to have. Now, if you're taking the test live, you could have questions that involve drawing. If you aren't taking the test live, if you are taking it virtually at home this summer, they're still going to want to find ways to test you on ray tracing, which means they're going to probably give you multiple choice questions that say, like, which is the correct ray tracing diagram? And if you're doing it live, they may have you actually drawing a ray diagram. So just heads up on that. But the process of ray tracing in general allows you to figure out what the image of an object should look like based on following the laws of reflection and the laws of refraction, which we'll talk about in a little bit later on. But the big idea is that any object like this carrot doesn't make its own light. The light that we see coming from the carrot, it's coming from some other source, the sun or lamp or whatever it is hitting that carrot, and then it has this diffuse reflections reflecting off the carrot, not like a mirror would reflect it back where it came, but all directions, because the carrot surface is really bumpy. So carrot sends light out in all directions, and then our eyes get at least 2 of those rays, right? We have 2 eyes for this reason. So 2 of those rays go into our eye, and those light rays are coming at slightly different angles because of geometry, because of the way that works. They're spreading out from the source of the carrot. So they actually they don't hit straight in the back of our eyes, they hit kind of off kilter from each other. And so our brain then triangulates back and says, oh, that carrot must be located here at the intersection of those 2 light rays. So that's how normal vision works. But when we put a mirror or a lens in the way and it bends the light, our brain doesn't know about bending. So our brain just tries to trace those light rays back and says, well, this is where my brain thinks this image is located. And so the process of ray tracing is basically this process of figuring out where would a person imagine this thing actually is. So an image isn't a real thing, it's a figment of our imagination, but we're trying to figure out where is that figment of our imagination located. And everybody agrees where it's located, which is kind of a cool thing. Everybody looking at a device agrees the image is the same location. So it doesn't matter which 2 light rays you use, in other words, all 2 light rays will produce a triangulation back to the same spot. So it doesn't matter how many eyes you have, at least as long as you have at least 2. Okay, so when you're doing ray tracing on a like a plane mirror, okay, all you got to do is pick 2 light rays, choose any 2 light rays that are going to leave from the object, and I usually pick the tip of the object on one side and the tip on the other because it's happening on the entire object. But if you know where someone's head is, you know where their foot is, you tend to know where the rest of their body is too. So we don't need to do ray tracing for every part of the object. We just do the top and the bottom, and then you can draw in the middle of the object in between. So the top of the carrot, we know you got to pick 2 light rays leaving the top of the carrot that will hit the mirror or the lens or whatever it is you're using, right? So there's going to be light rays that go in other directions. Don't choose one of those light rays, okay? Because that's not going to create the reflected image. You got to pick 2 of the light rays that are going in and hitting the mirror. So I picked these 2 light rays randomly, but it wouldn't matter which 2 you pick, you're going to get the same answer. We're then going to follow the law of reflection. So there's my normal line. We reflect it back out, okay? And then the key thing here is that you want to use the intersection of those reflected rays, okay? If you try to use intersection of any of these other random light rays, we're going to get a crazy thing. Or some people try to use intersection of, you know, the incident light rays, those ones going in. You only want to pick the rays that have hit the device and bounced off or gone through. Those are the ones you have to use for your ray tracing. So pick any 2, use the law of reflection to determine where they go after they hit the mirror. And then we use triangulation to figure out where would the brain think those light rays came from. And that's where that part of the object would look like it was, the image of the top of the carrot, okay? So if I was doing this ray tracing, I would do that. I would put a dot right here, and then I would do the second set of ray tracing from the bottom of the carrot. In this case, I picked a convenient ray. One of the nice rays of for mirrors is the ray that goes straight in, because that ray comes straight back out again. You don't have to muck with drawing angles and trying to get your angles right. So I like that ray. It bounced back out. But then any other ray you want to pick, let's do something crazy and pick this ray. I could do it really badly. And pick that just to show that if that was the second ray I pick, when I backtrack, so now I backtrack this ray, this straight ray is going to be along here, and I backtrack that other ray. Okay, and it looks like it came from right there. So no matter which rays you pick, we make the carrot in the same location. So we know the bottom of the carrot would be located there, and then at that point, I can just draw the whole carrot in because I assume it's all connected. Okay, questions on just the generic concept of ray tracing? Scale of 1 to 10, how good do you guys feel about the generic concept of ray tracing, given that it's been a year since you've done this? Okay, it's worth doing some practice. You want to be fast at ray tracing, because I actually use ray tracing to find answers quickly, because ray tracing can tell you lots of things. It can tell you upright or inverted. It can tell you magnified versus real. It can tell you virtual or magnified versus shrunk. It can tell you virtual versus real quicker than for me using that equation, especially if I'm not given values, right? if I just have a rough location, I just draw it roughly and I sketch it out really fast and get my answer. So from ray tracing, obviously, it should be pretty obvious whether the object's upright or inverted or whether it's bigger or smaller. The one that's worth mentioning is, how do we know whether an object is real or virtual from a ray tracing? And it depends on whether there's ever any of these virtual light rays, right? So in this case, the rays that we use, the rays that went into the eyeballs, did not actually cross each other, right? They look like they cross each other right here, but they did not actually cross each other. Therefore, it's a virtual light ray. Also, any image on the back side of a mirror is always going to be virtual. So just for the record, because you can't obviously have actual light rays located on the back side of a mirror. Classifying images. Oh, this slide is basically exactly what I was saying. You know, you can classify images. They're described as upright or inverted. Upright doesn't mean head up. It means the same orientation as the object. So if I was standing on my head, my upright image would also be standing on its head. Magnification, which was, we had that equation for it earlier. For plane mirrors, the object always ends up the same distance away from the mirror as the image was, or the image always ends up the same distance from the object. Therefore, the magnification of a plane mirror is 1. You look your regular height on the mirror, or at least as tall as you would look based on the distance away you would. So if you stand really far away from a plane mirror, you look tiny, but that's just because of distance. And then real versus virtual, and I think we talked about that in the last slide, so I'm going to keep going. All right, so this gets a little bit more challenging when we start talking about curved mirrors and curved devices. So mirrors are these specular reflectors. They don't bounce things in all directions. They bounce things always according to the law of reflection, but the normal line is changing direction as that mirror curves, right? So you can see at the top, this orange normal line is in that orientation. And then here it's like this. Right in the middle of the device, the normal line is going to be horizontal because that mirror is at a microscopic level, straight vertical at that location, but the normal line keeps changing, which means that depending on where the light ray hits this curved mirror, it's going to bounce in a different direction. Unlike a plain flat mirror where no matter where I hit, if I'm coming in, I always bounce off at the same angle because the mirror itself is flat. So you've got to keep in mind that the law of reflection is occurring, but that it depends on where on the device the light ray is actually hitting. In a concave mirror, or actually in a convex mirror, this is going to be the same. There's a few vocab words that you should have. There is something known as the principal axis. So when you hear the word principal axis, they are talking about the axis of symmetry for the mirror. So the axis by which you could, fold the mirror about itself and have it look exactly the same. So the principal axis is the one that goes right through the middle of the mirror and also goes through my focal length. It's going to go through this center location as well, which I'll come back to in just a minute. I mentioned earlier that mirrors can also be, or all devices can be categorized by either converging or diverging. And this would be a converging, which means to bring together, because you'll see the light rays all are sort of brought together when they are hitting different parts of that mirror. A good mirror, a parabolic mirror that is designed well, contains one location in space, a very small defined spot known as the focus. And the focus is the location through which light rays that are all coming in parallel to the principal axis, so they're coming in exactly parallel to that principal axis. If this mirror is designed well, they hit the mirror and they all reflect back through a single spot in space, and that's called the focus. To do this perfectly, the mirror needs to be parabolic. In the real world, most mirrors are not built to be parabolic because it's much harder to grind out a parabolic surface. It's much easier to grind out a circle because you can have just an arm that kind of grind. To grind a parabola, you have to have a much more complicated grinder. So most mirrors that we use, curved mirrors, are actually circular, which means the focus is just a little fuzzy. It's not quite as sharp and crisp as it could be. really precise technical equipment, telescopes, those kinds of things, go to the trouble to make a parabolic mirror because they want it to be really, really fine located focus. But in general, you know, the circle is if this is a parabola, you can see that, you know, the end of it approximates a circle. It's pretty close. So if we have a circular mirror, the location of that focus is exactly halfway between the center of curvature and the mirror surface. So if we were lazy and we made our mirror out of a portion of a sphere, which is what we mostly do. Oh, I do that really badly. Okay, let's try that. The center of the sphere is there, and the focus is going to be exactly halfway between there. So that's a good piece of information to have when you hear the word center of curvature. That's with a spherical mirror, and the focus is going to be halfway. Questions on this slide or the last slide? Anybody? Okay, so ray tracing for a concave mirror is not, I don't want you guys to think you have to have this procedure written out for all of your mirrors and devices. If you understand the big basic ideas of what is ray tracing and what do we do with it, you should be able to, on a test, do it for any kind of device, all right? The key thing for the ray tracing is that you always have to have two rays from each side of the object. And then you have to just follow the laws of physics with those rays and then figure out where the reflections or the transmissions look like they came from. And that's where your object is going to be. So for a concave mirror, if this is my object right here, it's spitting out light rays in all directions, and I could pick any two. But there are some that I would like to pick because they make a much cleaner, easier ray diagram. So there are two rays that I recommend you choose if you want to have the easiest, quickest ray diagram. So ray number one that I choose, and this is just because like these things are not drawn to scale. It's really hard to draw that reflection without having a tool that lets you get your normal line in exactly the right location or whatever, right? So you could use any rays, but these ones are the safest ones to use. So the first ray is the ray that goes in parallel to the principal axis, right? So that's that ray right there. And by definition, on our mirrors, every ray that goes in parallel reflects through the focus. So that one's pretty easy. It's going to reflect back through the focus. You'll notice this mirror is clearly not drawn to scale, because if you tried to draw a normal line here, it is not at all following the law of reflection. And this is what happens on the test as well. They're not actually drawing these devices to scale. And so this is why you have to use these special rays to make sure that you get the image in the right location. So incident ray goes in parallel to the principal axis, and it must pass through the focus back out. So that's my first ray number one right there. The second ray that I choose is basically, by the laws of symmetry, the opposite of the first ray. So because light is symmetrical, right, because law of reflection is symmetrical about a normal line, another rule is if a light ray goes in through the focus, it's going to be reflected out parallel to the principal axis. So the second ray I chose was this ray right here that went in through the focus. And then that ray is going to be reflecting out parallel to the principal axis right there. So that's my ray number two. And so then, just like we always do, we're trying to figure out where is this image going to be located. And the tippy top of that object is going to be located at the spot where those two light rays intersected. And so we get our tippy top here. Now, when we had the flat plane mirror, we went and did it again for the bottom, and we could try to do it again for the bottom, although actually it's going to be really tough to do this because the in through the focus is going to go straight on that principal axis and straight back out again, as is the other ray. So those two rays actually don't work if the part of your object is going to be on the principal axis itself. And this is why we usually just use this as a shortcut. We know that an object that is located on the principal axis the image of that object will also be located on the principal axis. So I'm not going to bother ray tracing the bottom of that arrow. I'm just going to assume it's on the principal axis, and it's a vertical arrow, so I'm going to assume it's vertical. So I just took a few shortcuts. I did have to do ray tracing to get the tip, but the bottom I just stuck on the principal axis to figure out where the bottom was, because I know that all the light rays that are going in here at some level are going to be bouncing straight back out. That means for sure the image is going to have to be on this principal axis somewhere of that bottom location. Does anybody have a question on this? Did I go too fast on any of those steps for anybody? Okay.
Wait, so does the, oh,
Yeah, go ahead, Connor. Great.
okay. Does the ray tracing, like these steps, do they only work for a concave mirror, or do they work for like a certain type of lens or something too?
My advice is not to view this as instructions for a concave mirror. My advice is to see the similarities for all of the devices, and each time you're doing it, just think about that device.
Okay.
So on concave mirror, when I think about it, I just imagine myself as a light ray. What am I going to do when I hit this thing? I'm going to bounce downwards through the focus. This is the only device for which this set of instructions, exactly as I've written it, works. But the same general steps and protocol follow for all the devices. And I don't tend to think of the protocol. I just think of the schemes. I think of the big broad picture of how does ray tracing work. So I don't know if that answered your question, but yeah, this is specific to a concave mirror. Convex mirror, so you can see here the similarities. Same thing, I'm picking two rays, right? And I'm going to pick two rays that are easy to use. Whenever I'm dealing with mirrors, I use this definition of, these curved mirrors are defined so that rays going in parallel are going to bounce out through the focus. On that concave mirror, they actually get to go through the focus. On this convex mirror, they just bounce out on an angle that looks like it came from the focus. So it's a little bit of a nuance there, but the same basic gist of the two rays that we're going to be using. So for this one, if this is my object, the two rays I'm going to pick that first ray that goes in parallel. And so by definition, anything that goes in parallel, but this time we're diverging, right? We're going to be bouncing upwards. And this is where I kind of think of the ball. The ball's going to hit that thing. Which way is it going to bounce? It's going to bounce up. Because in theory, there's also a focus over here, right? On this mirror, we could define two different foci, one on each side of this circle, basically. But so sometimes people get confused and they use this one, or they draw a focus on this side of the mirror. Maybe the problem doesn't tell you which side of the mirror the focus is on. It tells you it's 2 centimeters away, but it doesn't tell you if it's 2 centimeters away on the right or on the left. And so this is where you have to have the basic understanding of the throwing the ball. If you throw your ball, and Charter, I know you play a lot of tennis, you throw your ball and you hit that curved surface, think to yourself, am I bouncing down or am I going to be bouncing up and away? And that should tell you which of the two potential focal spots is the appropriate one to use. Okay. So for this one, the two rays it goes in parallel, and I know I need to bounce. I need to have some sort of connection to a focus. So and I'm bouncing upwards, so I'm going to use the focus on this side to bounce upwards. The second ray on this one goes in towards the focus, and then it bounces out parallel. There is a third ray that you can use here that uses the other focus, but I purposely didn't teach it because I think it sort of confuses the point. So there is a ray, if the other focus is located here, that you can draw that comes as if it came from this focus. I guess I have to put it there, and then bounces. Oh no, you can't use that ray. Yeah, don't listen to me. Undo what I just said the last 20 seconds. Ignore me. Use those two rays that I just mentioned. These are the safe two rays. These are the ones that you should be using. So make sure you're always using this focus right here, this virtual focus behind the convex mirror, and those are the right two rays. And so for this case, right, if these are your eyes catching these reflected rays, your eyes trace those rays backwards, and they end up with an image location that is behind the mirror. There was also a table that was given to you in the videos. It was like a real shortcut table, which I'm not posting right now because I don't love the fact that I even gave it to you in the first place, but it might save you some time. Anyway, long story short, whenever you have a diverging device, a convex mirror or a concave lens, the image is always upright, it's always virtual, and it's always shrunk. Okay, so those devices only create a very limited type of image. So diverging devices always create the same kinds of images: upright, virtual, and shrunk. The other devices can create a wide range of different kinds of images. The converging devices create all the kinds of images, so you have to be a little bit more precise about them. But this is a shortcut sometimes when you're dealing with diverging devices. Questions? Okay. Maybe I should have put this slide in a different order, but at this point in the original lecture series, I taught this equation, this thin mirror equation, because I wanted you to be able to do some calculations with it. And I think we've already talked about this equation, so I'm not going to go into the details again. But the units, incidentally, you know, our SI unit in physics is meters. But for mirrors and lenses, usually we're not talking about meters because these things are really small. So it actually doesn't matter what units you use as long as you're consistent. You use the same units for all three. So you don't have to convert meters into or centimeters into meters if you don't want to, as long as you use centimeters for all three, you're fine. A couple tiny notes about using this equation. Distances are measured from the center of the mirror or lens. I don't think that matters too much because they wouldn't give you a weird geometry one like that. But anyway, real object distances are always positive. Focal distances are positive for converging mirrors and negative for diverging. And then positive image distances mean they're real, negative means they're virtual. The last thing is just to be a little careful on the reciprocals. This is true with those circuit equations as well. Like, don't forget to actually take the reciprocal at the last step. People add up the image distance and the object distance, and they forget to take the reciprocal to find the focus or whatever object you're looking to find. So just remember that you have to take the reciprocal at the very end to find your actual solution. Questions on this equation? Okay. Refraction was the second big unit that we talked about in this optics chunk. And I've already previewed this, but whenever light hits a medium boundary, the transmitted ray is going to bend as it crosses that boundary. And you can see in here that some of that ray is reflected. So remember that rays hitting a boundary split into two pieces, one piece that goes in and one piece that's reflected. The reflected one's going to follow the law of reflection, but the transmitted one follows a totally different set of rules. The laws of refraction. Why does light refract? This is too much physics. It's too much physics. And I know I'm not the kind of teacher that would ever say that, but really this is like top physics professor at a university level physics, which is a little bit beyond where I ever got in my class. So you can read a famous book called QED by Richard Feynman if you really want to know. But in general, for us, we use this analogy of mud and pavement and cars or your fingers or whatever it is to figure out what just conceptually what the bends are going to be looking like. And so in the pavement or the fast medium, as we kind of mentioned earlier, we have a large velocity and a large wavelength. For all of these waves, that's always going to be the case. Whenever you're moving a large velocity, you have a large wavelength because they have that linear relationship. If you go straight into that medium, the velocity decreases and the wavelength decreases, but we don't get a bend because we went straight in, right? Both front wheels hit at the same time. However, if that car hits the medium boundary at an angle, one of those tires is going to hit first, and that kind of causes the car to veer one way or the direction or the other. So if we're coming in this direction, we're going fast, 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 and that first tire hits. I pictured my finger slowing down. I kind of use that finger as a pivot point, and so I'm imagining my fingers are the front two tires of the car and they're driving in. This one hits first, and then it grabs onto that mud and it kind of pivots me around, and then eventually both wheels are in the mud and we can kind of go straight again. So the bend happens exactly at that location. It's not like it curves in the medium. And when we are slowing down, we say we bend towards normal. If we started in the mud and we went in the other direction, okay, so we're going up this way in the mud, right? Now this tire is hitting first and it's going to speed up. So again, I kind of use the slower tire as a pivot point to run the faster tire around that thing to figure out which way it bends. And so when we are hitting a faster medium, the path is bending away from normal and veering up in that direction. Questions on this? Okay, so we use that Snell's law equation, which I described earlier, to calculate the angles that we are bending at if we have just a straightforward refraction problem that asks you to figure out what the angles were. But we use the idea of refraction to figure out what is happening in convex or in lenses, because it's this bending that happens when the light rays hit the boundaries of the lens that is what is actually making the light travel in a path that's not a straight line. The light ray bends at the front surface of the lens and at the back surface of the lens, but usually physicists take a shortcut and they pretend like it's a bigger bend that happens right in the middle. Okay, so you can see this is a shortcut. This is not what actually happens. The light is actually bending here a little bit and then bending here a little bit more. So it's actually bending at those two spots, but we're just drawing it, we're lazy. We're drawing it that way, but sometimes they give you a problem where you have to handle both surfaces separately. So just be a little bit on the lookout for that. The reason there's no like set lens design is because the lens design depends on the angles of the surface and on the material that it's in, right? It depends on how much it's going to bend. Unlike a mirror that everything reflects at the angle of incidence, the amount of refraction, the amount of bending depends on the angles that the light is hitting those lens edges and on the medium that is inside this. So on these diagrams, it's pretty critical that we are given a focus. We can't use this rule of like half the radius of the center of curvature for a lens because it depends on the materials as well. So we're always going to be given the focal length when we're dealing with lenses. So when we're talking about a convex lens, we will, because this lens is transparent, you know, we often will draw a focus on both sides of the lens because the lens is symmetrical. It wouldn't matter which side those are coming from. And unlike mirrors, sometimes we'll use both of these focal locations when it comes to drawing our light rays. Although I tend to use ray number 1 and 2 and not number 3, just for the records here. So the rays we use for convex lenses, ray number 1, okay, goes in parallel to the principal axis again, and then at a location, this is called the axis of, what is this called? Axis of symmetry, okay? So they're calling that axis of symmetry down the middle of the lens, and at that location, which isn't actually where this happens, but this is where we're pretending it happens, it bends through the focal length. Okay, so if you're a well-designed convex lens, all light rays going parallel into you are going to bend, all of them are going to go through the focus. So it doesn't matter which light ray you pick that's going in parallel, it's going to always come out through the focus. So that's what I use for light ray number 1. And the ray I use for number 2 is actually a ray that would bend twice. It would bend on the front surface and the back surface. But those bends actually exactly cancel each other out because one of them is away from normal and the other is towards normal. So functionally, what happens on ray 2 is it starts at the object and it goes straight through the center of the object. There is, by the way, one on mirrors that can be done a similar way. So you can always draw a ray that goes to the center of the mirror, but it doesn't go through the center of the mirror. It's going to bounce off. You know, the normal line is like this. And so this is another ray that can occasionally be used on mirrors. I don't tend to use that ray as much because I have to approximate these angles, right? I'm not given, it's easier to draw through a location, like through a focal point, than it is to have to try to make two angles similar to each other in my mind. But as far as lenses go, drawing that line straight through the center is actually a really easy one to do, because you just take your ruler and you stick it on the paper and it's a straight line right through the center. So 1 goes in straight out through the focal, 2 goes straight through the center. Those are the 2 I would use. And then wherever those 2 things converge, just like always, is going to be that location on the image. If my object's bottom is located on the principal axis, I'm going to make the image's bottom on the principal axis as well, and that allows you to draw your final image. You can use that image to figure out all of the characteristics of this image, right? So in this case, we have our image is inverted because the top is down. It is going to be magnified. I can tell that image is further away from the lens than the object is, therefore it's going to be taller as well. And this is a real image because those light rays did pass through a single point where that image is located, right? Your eyeballs in this case are located out here. This is where the eyeballs are catching the light, and those eyeballs trace those light rays back to that blue spot where both of those light rays actually pass through. So this is going to be a real image. But convex lenses can create all kinds of images. They can create virtual images as well. So it's worth going through some practice. And I put at some point posted a bunch of practice problems for all kinds of lenses and mirrors, and those might be a good thing to do one more time as you prepare for the exam. And then our last situation is the concave lens, which is a diverging device. So light rays are going to go in parallel and then bend away from that device, away from a focal length located on the front of that device. So you do the same thing as always. You start with your object, you pick your 2 light rays. The first one goes in parallel. This is one people mess up all the time, right? Because they see this handy dandy focus here and they're like, oh, that seems like I should draw that line through there. But remember, this is a diverging device. So we got to make sure we bend our light ray the right direction. So I would have to use this focus. I know I have to bend through a focus, but I don't have a focus on the right side. So I'm going to use the one on the left side and draw and set up your ruler so that it comes from that focus and draw it straight out. And then I love this line that's super handy that you draw straight through the middle. Okay. So when I think about these rays going through my eye, it's kind of interesting because trace them back, the point they intersect is right here, and that intersection contains 1 virtual ray and 1 real ray, right? It's a real ray number 2, but ray number 1, it's virtual. It's not the actual ray number 1. It's just where it looks like ray number 1 came from. So my brain thinks the image is there, and because one of the rays was virtual, this is a virtual image as well. You can't make a real image out of any virtual rays. If you have any virtual rays, we've got a virtual image. And this is another example, as I said before, whenever you have any kind of diverging device, so including concave lens, the image is always going to be diminished or shrunk. It's always going to be the right way up, so it's upright, and it's always going to be a virtual image that you make as well. Okay. Questions on that? So we have gone to 12:56, which is just about right. I will post this slideshow so you guys have access to it as well, just the images if you missed anything or I went too fast for anything. I have a bunch of questions on there that are those ones, yeah, that involve some multiple choice questions about that would be relevant to this unit. But really the first thing I would do if I were you guys is go and do the progress checks that are on AP Central, because they'll give you the feedback on how you do on those things. If you feel like you need more practice with optics, let me know and I'll make sure you have some optics problems to cut your teeth on and keep working. Last minute questions before we wrap up. Or in the chat, say no questions if you don't have any, just so I know you're still here and I haven't cut off a half an hour ago. No questions? Okay. How many of you guys are coming back live and hybrid? Anybody coming to campus? Handful of people? All right, well, if you're walking down by the science hall, I know we're not supposed to like mix cohorts or whatever, but if you pass by, please at least poke your head in and wave and say hi, because I didn't get to see you guys at all in the fall, and I hope things change, but it is what it is. But come see me at room 235. I'm way down at the end of the hallways, and I miss all of your shining faces and amazing personalities. And I know you guys are gonna have a challenging month ahead of you getting ready for all this, but please let me know if there's anything I can do to help and support you guys. Okie doke. So I'm gonna go ahead and stop the recording, and I'm happy to hang out for a few more minutes if anybody individually has questions, but otherwise I assume you guys are gonna be off to your whatever you got going on the rest of the day. It was great seeing you guys.
Thank you.
Thank you, Ms.
Thank you.
Nichols.
Have a good day.
So I had a question about one of the progress checks. I just did the first one for Unit 6, and I had a question about the second one. It was talking about the ratio of object distance and image distance, and I didn't know how to do it.
That's that magnification equation.
Hmm.
So the ratio of object distance to image distance is going to be the same as the ratio of object height to image height. So let me open it up, and I will, I'm happy to look at the actual problem if you want, but my guess is that you had some information about the object's height and the image's height.
Not exactly. It was I've seen it before. I'm pretty sure this has been a question before, but it was less than or greater than, the ratio is less than or greater than a number.
Okay.
And I don't know where the number comes from. So
Yeah. Okay. Let me take a look. So that magnification equation probably gets used with the thin lens equation. So if you aren't given, that's an annoying question to me, because there is a cheat sheet table that you can memorize to have the answer at your fingertips. But I don't think that they should give you problems like that reward someone having memorized a useless table of information. That pisses me off. But let me just take a look at the problem. And I don't have those tables memorized. I never saw the value in doing them. What I would probably do is a quick ray tracing diagram, or I would throw numbers at the thin lens equation to get something that would be close enough. Which one is this? Unit 6 progress check?
Part A.
Part
And
A.
then it was question 2.
Okay. Yeah, so this is one of those annoying things where there is a table that has that has this answer in it basically, but that's not how I do it. Okay, so how would I solve this problem? This is not going to be the fastest way to solve the problem, but we're going to do it anyway. Okay, so I would do a really quick ray tracing, Maylee. I love ray tracing. So I would throw my ray number 1 in there, right?
Mm-hmm.
And ray number 2 . Okay, so that's enough for me to see where this image is, right?
Mm-hmm.
And so it's really clear to me that the image is going to be, well, you tell me, how would you classify the image?
I think it would be magnified, so it's bigger than the object, and then it's
Yep.
also inverted.
It's inverted, and is it real or virtual?
Is it? I kind of confuse these sometimes, but is it I want to say virtual, but
No, it's real because these are real light rays passing through each other.
Okay.
And by that, I mean, they're not rays from behind the mirror. The rays that went to my eyes actually passed through this spot where I'm putting the image. Those 2 light rays literally I drew a solid line through those light rays through that spot where the image is made.
Mm-hmm.
Okay, so it's real. That's not part of this problem, but it's good to know. Okay, so the only part I care about here, though, is that you said it was magnified. It's bigger, right?
Mm-hmm.
So that magnification equation is SI over SO. So it's bigger than what?
I guess it's bigger than 1.
It's bigger than 1, but less than infinity, right?
Yeah.
Yeah, bigger than 1, but less than infinity. What the questions ask for is S over SI, which is the reciprocal. So 1 over some number, put a number in there, 3, some number that's bigger than 1, but less than infinity. And that's going to tell you S over SI is not going to be less than 0. It's going to be somewhere in this range of 0 is less than that to 1. So the answer should be B, I think, right?
Yeah. It's, yeah.
Do you see where I got that now or not? Or did I lose you in that last step?
I kind of got it, but I answered C. So like, I was wondering how you could like kind of knock out that answer because it's either between 0 or 1 or 1 or 2. So
Okay.
like,
So you said SI has to be at least what?
it has to be at least bigger than 1.
So SI, yes, it has to be bigger than 1, right? So let's make it 1.1. Or it could be way bigger than 1, right?
Mm-hmm.
So 1 over, like, let's say 1,000. Okay. What is 1 divided by 1.1? Give or take.
Less than 1.
It's less than 1. And what is 1 divided by 1,000?
Also less than 1.
Also less than 1. Bit bigger than 0, but less than 1. There is no number that we would take 1 divided by it and get bigger than 1 because this number has to be more than 1. Therefore, the reciprocal of that number has to be less than 1.
Okay.
Yeah. So the tricky thing is that they didn't ask for M. They asked for the reciprocal of M.
Oh, okay.
Yeah. Because M is SI over SO, and they asked for S over SI.
Okay. I
Okay.
think I got it. Yeah.
Yeah.
All right.
I
thank
agree.
you.
That's a tricky kind of problem to do. Did you
Yeah.
understand the other ones that you missed on that?
I think so. Hold on. I got another one. Okay. Yeah. That was the only one I really had a question on.
Okay, great. Well, good for you. I know you're taking the test early, right? You're taking it on the 7th.
Yeah.
How are you? What other tests are you taking? Are you taking another test that week?
No, I have I'm taking AP Lang, but that's like the next Wednesday. So it's not that bad. I mean,
Okay.
there's
How's your anxiety and stress on a scale of 1 to 10? How are you feeling?
Well, actually I feel pretty good about physics. I think I could probably knock some stuff out. There's only like conceptual stuff for like 2 units that I need to work on. It's
Okay.
just the AP Lang. So it's like I need to like learn how to budget my time, I guess. So I'm like medium. I don't know, like a 6.
On that one. Yeah, it's I remember my AP English teacher just saying like you either get a 5 or a 1. It depends on whether they can read your handwriting. Like I write so fast, so that was like a huge benefit to just be able to write fast. But then there's these little things that come up, like you get a random question that messes you up or whatever. So
Yeah. I don't know.
budgeting time.
There was the difference between like online and in person. I mean, I don't think I can change it right now, but it was like online you can't go back to your question, but in person you have to write everything, and I don't know if I can like do that in the time limit. But I mean, I don't know. I think
If you want to change, I don't know for sure that you can, but I do know that the date that they gave me was the 23rd and I posted the link. So if you wanted to think about changing, make sure you do that in the next 2 days.
Okay.
But I'm glad you feel pretty good about physics. Are there any particular, anything you need from me as far as review for physics, or do you feel like you have resources that you need?
I think I have everything I need. It's just doing all the progress checks and then maybe looking back on like older tests.
Yeah, I have this. Mr. Venato just gave me this. I don't know why. I haven't really looked through it yet, but I have, books with lots of practice problems and things explained. And so if you either wanted to borrow a book or needed a section of a book, let me know.
Okay. Thank you.
Okay, but otherwise, I'm not worried about you either. I mean, I think crazy things could happen, but I feel really good about what you know and what you've learned. And, I expect you to score well. And if you don't score well, I still like you and know you've, learned a ton of physics and that you'll really use it down the road. But I have, I've seen a lot of students and I think you're really strong. So,
Thank you.
all right. Well, good luck with everything else. Let me know if there's anything you need. Okay.
All right. Thank you. Bye.
Bye.